guys, I'm going to go ahead and get started. Quiet down. All right, so last class we discussed aromaticity. Just going to spend a little bit, so that'll be the next couple classes. So I'm just going to sort of rehash a little bit about what we discussed on aromaticity, put in some additional context that I was sort of noticing I think we should discuss. And then we'll start to get into reactivity of aromatic molecules, which again, within sort of conjugated pi systems, there becomes some interesting features to them that you guys should be able to understand, but we'll sort of discuss. Right? So everybody's going to be able to look at a molecule like benzene and immediately sort of identify a molecule like this as aromatic. The features of being aromatic, right, are that structurally it becomes very planar, so that all the bonds can sort of align, right? So it becomes a very stable sort of aromatic system. It should be easy then to take that and sort of recognize it in some other contexts as well. Where the challenge will often come in identifying aromatic molecules is, again, once you start to do things that vary from benzene or from all carbon-containing cyclic structures. And so some of the examples that we discussed last week would be things, again, like furan. Again, furan, I think it's a little bit difficult to sort of see this, in part because one of the things that you guys often like to do is start drawing resonance forms and expect there to just be a quick flow of electrons around here. And actually, I got somebody that came afterwards that was asking a little bit about this. He said, well, what's the aromatic, sort of what's the resonance structure of this? It sort of shows that. And again, it's not necessarily one like benzene that wraps around, but you could certainly imagine a resonance structure where you sort of separate your charges. And sort of this method, and then you can sort of continuously go around this system. Put a negative charge there. All right, and so you can sort of draw these resonance forms, and certainly I sort of understand that this doesn't necessarily look as neat as some of the other ones that we've seen. So again, in cases like this, I think generally the best thing to do is consider this sort of overlap of pi orbitals in this system. And I just often think that it's best to sort of do this. It helps you recognize some important features, I think, of these molecules. Right? So in this case, what you're going to have is you have the two lone pairs on oxygen. One of those lone pairs will subsequently adopt the p orbital characteristic, right? And so I think it's this kind of diagram that helps illustrate, again, why this is aromatic, how those orbitals all interact with one another, in addition how there's sort of 6 electrons in this, right? So that is sort of important. We saw the same thing with cationic species. Actually, sort of one quick sort of point, and you'll sort of see this from time to time. So here's cyclopentadiene, right? One of the things that those of you that may go further into organic chemistry, specifically within perhaps advanced or organic classes, if any of you become interested in that, start to use derivatives of this, for example, as ligands, and the idea here, as you might imagine, right, is that this molecule isn't aromatic, but you simply take it and treat it to a base. And so these are fairly acidic protons, certainly much more acidic than your average carbon-hydrogen bond, in part, again, because you generate sort of that aromatic system, right? And so now we have a system where what does this equal? But it starts to look like something of this nature. So again, it is charged, but it does become aromatic, and specifically in a lot of organometallic chemistry, this is often used as a ligand for various metals, and so it's fairly popular. It's also just another good example of sort of aromaticity in chemistry. I just want to show a couple additional examples. We also mentioned cation interactions as well, so things like tropolones, and such, so systems where you may have carbonyls in them, right? You look at a molecule, like this, right? This is tropone. Okay, and this is a compound that on its surface might not necessarily look aromatic, but you sort of recognize that there are resonance forms of this. Right, and now what you have is what's known as a tropylium anion. And as you can imagine, right, that tropylium cation is very highly stabilized by this sort of resonance throughout this system, right? So you can push all these electrons around, right? Ultimately, what it ends up becoming is sort of shared throughout all those systems, and so you have just sort of a system where that positive charge is shared throughout that all. You'll often see, some of you may have already sort of jumped at this, you'll sometimes see, if you haven't, now you have, you'll often see, because we're seeing this now, we'll often see benzene drawn like that as well. That's something that I didn't mention earlier. That sort of, it's a very common drawing of aromatic molecules simply to show that this resonance form isn't necessarily really what this is like. Again, it's sort of shared throughout all of those equally, and so this is a fairly common way to draw benzene. In the same way, this is a common way to draw tropylium ions. Again, there's just one additional one that I want to discuss, and it's in part because we're not going to get into nucleic acids really much at all this semester. We might touch upon it towards the end, but you guys are all going to take, many of you will probably take biochemistry courses, and in the biochemistry courses, what's going to come across is, we had a course where we discussed a little about amino acids, and so that's going to be one subunit that's going to be involved in proteins and enzymes and the like. But another really obviously important building block in biological settings, right, is nucleic acids, and so what you'll see in these nucleic acids is there will often be what they call sort of base pairs in these, and so one that you guys may have heard of, I'll just draw the structure to make a point, is sort of adenine. So this molecule is adenine. It's just one example of one of the nucleic acids that you'll see. Again, if you're curious about all of them, you can go and look them up. They're all tend out to be aromatic. But on the surface, this molecule might not necessarily look, right, aromatic, but it turns out that it is. So let's discuss and describe why this might be aromatic. What we have here is something that can happen from time to time, right? With say, for example, amides or esters. I guess we'd call them lactams or lactones in these cases. But again, that's an amide embedded in a ring. And so one way to consider this molecule slightly differently is actually as, you can draw as a lone pair, but in this case you can actually show the resonance as well, which I think sometimes helps. Okay, it's a charge here, and so this is the resonance form. You begin to see a sort of 6-electron system, but it actually extends, in fact, beyond that. It extends all the way throughout the system, right? And so in addition to the 6 electrons that you have in here, right, you've got the 2 electrons here, which takes it to 8, and you get the 2 additional electrons there that take this to 10. So this is, in fact, a 10-electron system. Again, if we think about the 4n plus 2, that would represent n equals 2, right? So that's an aromatic system, and this becomes very important, as you'll see, those of you who get to take biochemistry courses, because the effect of this aromaticity, right, is that the system is rendered planar. And by fact of that being planar, it becomes very, 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 very important, and in part, well, for a variety of reasons, but certainly the way that the amino acids are set up, they're rigid, and as you guys start to see things like the duplexes of sort of oligonucleotides, you'll see, this sort of system of these wrapping around one another in a sort of a planar fashion. It's also important in part because there are a lot of compounds. For example, benzene, right, is actually toxic, cytotoxic, or sorry, carcinogenic, in part because you can begin to disrupt those interactions and create bulges, which, again, that's for sort of more biochemistry. But again, I think the point that I want to sort of bring home is that sort of base pairs that you guys will see in biochemistry courses, they are aromatic, and so when you start seeing molecules in biochemistry, and you start seeing the double helix and everything else, and you see them flat, you'll sort of know why now. It's because of that aromaticity. Okay, so that's really all I wanted to discuss in terms of structures of aromatic compounds. Okay, so you should all be able to, you can expect to get questions on exams, and I guess it would be tough to have one on a quiz at this point, but you could probably expect a question on an exam where you're sort of given a molecule and you're asked whether it's aromatic, anti-aromatic, or not, or neither. So again, that's the aspect within that. Recognize when molecules are aromatic and why. Now, these molecules all also have very highly conjugated systems, right? And the nature of that is that change is fairly remote. Structurally, you can have fairly major impacts. And so, if you think about a molecule like phenol, all right, this is an alcohol in essence, but it's sort of has its own name, in part because it is an aromatic OH. That OH is in conjugation with everything else. So what it's called is a phenol. You guys know that another word for benzene, right, is a phenyl group when it's discussed as sort of an appendage, that term phenyl. So this effectively comes from phenyl, right, and alcohol. And in terms of the nomenclature, that's where it can come from, the phenol. Phenol is sort of an interesting molecule in part to discuss and start to get into the chemistry of aromatic compounds, in part because what we can start to think about is the sort of pKa values of phenol versus a few other similar alcohols, or OHs, I should say, that we've seen in the past. So something like, right, ethanol would be one example of an alcohol. This is what we would think of an alcohol. Certainly you've seen OHs in other contexts. For example, acetic acid, right? So, and as we saw previously, right, acetic acid is much more acidic than ethanol, right? Ethanol has a pKa. This is for the acidity component, so this is going to be O-. pKa is somewhere around 16 or so, right? Whereas the pKa of acetic acid is somewhere around 4 or 5. Just 5, I guess. 4, I like 4 better. Again, in that ballpark. So fairly dramatic change between the two. And again, we know this because looking at the conjugate bases of these, right? We draw the conjugate base of this, and we have an ethoxide. That's an O-, and the oxygen's okay, electronegative, so certainly you can deprotonate it much easier than you could, say, for example, an NH or CH. But it's much, much easier to deprotonate a compound when you have the resonance forms, right? Because then that negative charge is spread equally throughout, is spread throughout the system. In this case, by deprotonating it, right, you have the two resonance forms, one where you have a negative charge on the oxygen, the other one where you have a negative charge on this oxygen, so that negative charge is shared fairly equally among them. Phenol also has resonance forms when you sort of deprotonate it, right? The sort of deprotonated form is that one there. And again, we can begin to imagine resonance forms of this where we push this around the system, right? So all right, and then we can keep pushing these around this entire system. So there's multiple resonance forms that you can imagine from phenol. None of them are necessarily as good as the other one with carboxylic acid, right? You're not necessarily sharing it to another, you're not necessarily giving it to another oxygen. It's a series of carbons, but it's still better than what we have up here, right? There at least is that resonance form. So the pKa of phenol is actually somewhere in between these two. It's got a pKa of about 10. Right, which sort of demonstrates that it's certainly more acidic due to those resonance forms than, say, for example, ethanol. First part of this. The other point that I want to make, though, and this is one of the factors that will come up in terms of reactivity that I think is worth mentioning. And that's that when we deprotonate this species, as we begin to push these electrons around the system, I want you guys to notice something. And that's that what we really have in terms of additional resonance forms is really only two. Right? We can push the electrons onto this carbon, we can push them onto this carbon, and again, if we kept going, we'll push them onto this carbon, but this carbon's the same, right, as this carbon here, okay? These end up having effects on the reactivity that a molecule like this might take on, and again, this will come up within our sort of chemistry, but when you sort of put these all together, you really only have, when we think about charges, you really have charges in two of those systems on here. Again, there's symmetry to this. Again, we'll sort of discuss these, ultimately have names that we'll get to in a moment, but these are kind of what we consider relative to this, the ortho position. These will be called the meta position, these will be called the para position. So this oxygen effectively puts a fairly reasonable negative charge at these two positions. well as this position, but what it's not going to do is put that charge at these two positions. In part because, or at least not nearly as much, in part because you can never put that resonance form in that position. And this is something that's going to be important. Resonance and seeing resonance forms is an important component of learning about aromaticity. Okay, it does find its way into pKa, and so we can sort of discuss that a little bit. So if you say, for example, put a substituent on a phenyl group like this. All right, so you put a nitro group on here. That nitro group is in conjugation with the rest of the pi system. But importantly, you can actually, if you were to deprotonate at this position, you're in a position where you can resonate throughout here. So if I were to deprotonate this phenol, right, we can actually have a resonance form here where we can push these electrons all the way up into that nitro. Okay, you guys see that? All right, and so you can get to a resonance form that looks something like this. Okay, this is certainly a better resonance form than anything that we have with just phenol itself. And so, as you might imagine, that's going to have an effect on the pKa here. In fact, making it more likely to want to be deprotonated. Nothing too dramatic, but it is certainly there, and it's measurable. But the pKa of this is going to be about 7 or so. Okay. And it's important where that nitro group goes, because this is, again, we'll get to orthometaparin in a moment, but this is what we would call paranitrophenol. If we went to the meta position, there would really be no way to delocalize those electrons into that nitro group. So while it's inherently inductively withdrawing, which would certainly have an impact on the acidity, it doesn't necessarily have that same resonance donation. There's really no way, that you can push them up that way, right? So you push them onto this carbon, you push them onto this carbon, you push them onto that carbon, but you can never get that negative charge on the carbon. It would be necessary to have the resonance go back into that nitro. And so there is actually a fairly substantial difference here in terms of pKa values. This is closer to 8. Again, it still has a withdrawing effect. Nitro is a very, very good electron withdrawing group. But you'll notice there is that difference. Even though proximity-based, right, this nitro is closer to where that negative charge would be. So even though this nitro is closer, which means that inductively it would have a better effect on that, it turns out that having a nitro at the para position is in fact better at stabilizing this negative charge, again, because of this resonance form that you can sort of draw. Okay, does that make sense? And so it's going to be really important that you guys are able to draw resonance forms through aromatic systems for the material that we're going to cover in the next couple classes. Yeah?
Would it be more acidic in the pure form, or would it just stay the same pKa value?
In the para form?
Yeah, you said it's more stable.
I'm not following. Well, the pKa is 7.
No, I'm asking, like, you said it's more stable in the pure form, the nitrobenzene.
This is more stable.
I'm just asking if it would be more acidic at that pure form.
Yeah, that's the point that I'm making.
Okay.
Yes. That was the whole point of this. Is that this is more acidic at the para position. Likewise, you might imagine at the ortho position, it might be even better than the para position. I actually don't have those pKa values down, but you could probably predict that because it would be both closer in proximity as well. So we just discussed meta para, we discuss sorry, we discussed meta. Para, what we didn't discuss is the ortho position. So if it was at the ortho position, then again, it would also have that resonance stabilization, but it might be closer. So I'm actually not sure what the relative pKa differences are in that case, but you guys could probably guess that it would be probably as good as this, maybe better based upon closer proximity of the group. If it wasn't, then maybe there's some repulsion going on or something. But again, that's the point that I wanted to make, is that resonance and drawing resonance throughout aromatic systems is going to be really important here. So hopefully by this point you're really good at recognizing and drawing resonance forms, because we're going to be drawing a lot of them. So, okay. All right, so we're going to start getting into reactions now of aromatic systems. And in many ways, the reactions that we're going to see are largely extensions of, for example, alkene chemistry, right? So, except with a slight difference, right? So, not all of them per se, but many of them will be, because you can imagine that one difference between reacting with an alkene and reacting with a benzyl group or an aromatic compound is that you're going to have to break some aromaticity. So there's probably going to be a much higher energy barrier. Yet, in terms of mechanisms, you could at least start to reason a lot of the chemistry, right? So if we were to take an alkene and react it with bromine, right, we all know what's going to happen. And that's what we're going to basically add bromine across this system. And the reason, again, is because the mechanism is going to involve bromonium formation. And then what will happen is that other bromine will come and attack here. And the reaction of a benzene group isn't going to be exactly like that, but let's just sort of imagine for the start that we did the same type of transformation and start to think about what could happen. So ask that same question: if this could react with bromine, you guys could all probably predict, at least the first step of this mechanism, if I told you they were to react. If I said bromine and benzene react together, which is, we'll get into a moment, they don't, but let's just imagine that they do. You would probably all be able to draw something like this. Right? You might all be able to draw something that looks something like this. The question then becomes, and you can do a couple things here. The next sort of question becomes the bromine that's going to add in to displace this. You do have this Br minus. And this Br minus could perhaps add into the system, for example. But to the same extent, there's a very downhill energetic barrier here to re-aromatize the system. Again, driven by this idea of aromaticity. So however you guys want to draw this, sometimes it's easiest to say, for example, draw it as the open form. Remember, these are kind of pseudo-resonance forms of one another. Right? And rather than a bromine adding to that position, what can happen now is the bromine can serve as a base. And again, it's just going to be a much more energetically downhill process. So rather than adding bromine across the system, you might imagine that instead you might generate HBr. Okay? So again, this isn't exactly what happens, but this is a good place to, I think, start thinking about the reactions that we're going to see with benzene. There's going to be a lot of reactions that are effectively this type of mechanism. Benzene is going to react with an electrophile, right? You're going to generate a positively charged species in a way, but by virtue of doing that, what's going to happen is you're rapidly going to then deprotonate it to redrive aromaticity. So this kind of stepwise process is going to be really the mechanism behind almost every single reaction that we sort of see. Now, I told you this doesn't actually happen. right? And so I'm just sort of showing it as an example to sort of understand mechanistically the driving force behind a lot of the reactions and that sort of similarity. It's going to be the same nucleophilic addition that you can imagine of an alkene within this system. But the problem is, right, is that going back to this sort of idea of aromaticity, this really isn't going to happen, right? It's just not going to happen, but serves as a good sort of starting point. The reason why this doesn't happen is to overcome this barrier, you need to break aromaticity, right? And so it's going to be a much, much higher energetic barrier to overcome. And so when you're doing aromatic chemistry, what you need is you need something even better. You need things that can, in fact, activate electrophiles. Bromine by itself isn't enough. But when you use bromine and you activate it and make it an even better electrophile, then it becomes reactive. And so what you'll generally do here to get this transformation to take place is that you'll use bromine, but you'll give it a Lewis acid as well. And the common Lewis acid in this, sometimes you'll see it, aluminum trichloride is usually used for some of these other things, but oftentimes what we'll see is iron tribromide, for example. These are all going to serve the same feature, okay? They're going to effectively coordinate to the bromide, right? So you can imagine these two guys sort of coordinating. So you'll get this sort of iron tribromide will sort of start to accept some of the electrons from one of those bromides. Right? And you can imagine, in fact, drawing it something like this. So it's sort of a Lewis acid that's going to activate it. That net result is that what you now have is something you can imagine. You can draw an additional resonance form where almost literally, I don't say literally, but almost literally, we sort of begin to think about this as a cationic bromine source. And again, this isn't necessarily exactly what's going on, but I think within aromatic chemistry, I'm going to sort of tie everything to these more cationic species. So we're going to draw the electrophiles oftentimes in cationic forms as our way to illustrate that we need something that can make them this electrophilic. Okay? And under these conditions, then what you will do is, in fact, get the bromination, and it will work fairly well. All right, so from a mechanistic standpoint, I think the trick here, and the thing that can sort of sometimes complicate bromination chemistry in this regard is over here you'll notice that the byproduct is HBr. Okay, and I think this is oftentimes where people get tripped up, and unfortunately I don't have a great, clear way to explain this to you guys from the mechanism standpoint. You can imagine that if after treating this with Br+, because you want to be able to draw something, right? What I would probably do if I were you guys, and I'll just draw in this form here, is that you do have this FeBr3, and so if you need something to draw, what I would say is I will be cool with you guys just either keeping with a Br-, so this is just so you guys can have something to draw. You can either stick with the Br-, which would have otherwise been here, or if you'd rather, you could do something like this. Again, I don't even know exactly which one is more kosher than the other. But I think either one is probably fine. Something needs to sort of eliminate that compound. So if either you imagine the Br- and FeBr3 being closely associated with one another so that it reacts from the bond between the two, or if you imagine the dissociated version itself. I would probably say, as you guys might imagine, that the Br-, just imagining this, I would probably just sort of think about it that way. Just imagine that the FeBr4 is negatively charged and it produces dissociation. At least that way, you're not having to draw electrons moving from a bond, which I recognize is not something that we like to do that much. So I would go ahead and do it from the bromine. Okay. Does that make sense? Yeah.
Use potassium bromide, PBr3.
I've seen it used, but only under use potassium bromide. You might be able to. I'm trying to remember why. But yeah, for some reason I'm thinking that you can, but I'm not sure at this moment. I've never so I'd have to look into that. But it's possible. You know, that's sort of drawing a parallel. That's usually where we use I don't know. I can't mechanistically see how that would work. So oftentimes you use that as an alternative to HBr, for example. But potassium bromide is a salt. It's inherently nucleophilic, so you then have to somehow turn that Br minus, right, inherently into a Br plus. And the thing that's interesting about bromine, and you actually see this with HBr, and we see it, for example, with HBr. Sometimes once HBr, these things start to go bad. There is a redox process where it actually can form Br2 in situ. And that's probably what's happening if it can be done. But I would just stick with this. Keep it simple. All right, so this is one example of functionalizing these compounds, and you might imagine that similar types of transformations can take place with other halogens, right? So chlorine, for example, you might go ahead and imagine chlorine, and sometimes you can use chlorine with iron trichloride, or sometimes even aluminum trichloride. But sort of, I would just say recognize that this is simply much in the same way that we discussed halogens adding across double bonds. You can sort of draw that same type of parallel within here. So but again, what you would need to do in this case is you would need some type of a sort of a Lewis acid in this case. So again, in part due to redox processes and the potential for trace amounts of chloride or bromide to actually dimerize in the presence of oxygen, you may want to stick with the same thing. And that makes it easier to keep together, right? If you're using bromine, use iron tribromide. If you're going to use chlorine, use iron trichloride. You don't really see iodine used that much in this. It can be done, but it's not quite as popular in part because iodine is less reactive inherently. Fluorine as well, there's usually reagents. So I would just stick for this case with bromine and chlorine and leave out iodine and fluorine for now. So let's just say X equals fluorine, bromine. But it's worth sort of recognizing that you know, it's not that big of a stretch to imagine it with iodine, right? And I'm not sure if it exists with iodine or not, but if it were to, you would imagine. I'm sure there is a way that you could do it. Whether they be under the same conditions or not, I'm not sure. But so for now, let's just focus on chlorine and bromine. Now, what we'll sort of see moving forward from here, again, we've just started with halogens, but again, really what this is going to amount to is a lot of chemistry where you do this exact same process. Okay. And some of the really popular ones, and there's really a sort of a bunch of these, but they're all going to follow through, I think, this idea of trying to generate cationic species. And so some of the ones I like to start with are nitration and sulfonation. Okay, so it turns out that if you take this compound, and again, I'll explain the details behind these briefly, is that if you take these and treat these with nitric acid, let's just start with nitric acid. So this molecule here is nitric acid, right? So that's nitric acid. Just decided to draw it out because sometimes it's easier to see that in part because once you start getting the sort of zwitterionic species, I guess it can be confusing. What you need to actually do this transformation is sulfuric acid. So as it turns out, if you take benzene and you treat it with nitric acid and sulfuric acid together, what you end up getting to is the nitration process. Okay, and so in this case, unlike the iron trihalide that we had, in this case the activator is in fact going to be sulfuric acid. Okay, and the way that this transformation works is, again, it's largely, I think it's worth thinking about it in terms of liberating a cationic species. And in this case, that cationic species stems from effectively protonation. Okay. And again, this is a sort of a reversibility issue. You might imagine that this compound is going to react with this, that it would first protonate one of these two positions. But I often like to think the best way to sort of draw this and reason it and move forward is sort of generate this, and this is in fact what happens, you generate this HONO species, where you do a dehydration process. You generate a super activated compound. Okay, so you can imagine once you protonate this species, you can actually eliminate water. And generate a cationic species there in terms of the nitro. This actually goes a step further, and you actually protonate this. You might see this idea of HONO. For some reason, that's easy for people to remember. I don't necessarily, from a mechanistic standpoint, think that it's 100% necessary, but with further sulfuric acid, you'll actually activate it even further. And this just has one of those names, not name, but it's literally what you're sort of generating. So that sometimes people like this because it helps them remember it. Oh no, I don't know, it's a nice sounding name to sort of imagine this reacting. I don't like how it looks because you've got two cationic species next to one another, but it does at least illustrate how active this compound is. Ultimately, I often like to just draw it directly from this one, in part because that gets you right to the product. But you can tell in both cases that what you have is an activated species, and regardless of which one it functionalizes with, I'll just choose this one because I think it's not as weird looking, if you will. Right, you get a molecule like this, and then, again, what's going to deprotonate it? We can imagine a couple different things, right? We can imagine HOSO3-, for example, regenerating sulfuric acid, or you can imagine from the nitric acid. But the net result, right, is that you are going to generate this compound. If you choose to go through HONO, then you simply need to deprotonate at the last step. So again, either one of those is fine. I like to just go through this, even if it's not, technically what's going on, simply because it gets you right there. It makes sense of the reaction. And I think, from my standpoint, I think what's important to recognize is that you're activating this compound. And I think it's easier to see that this is an activated species, even though, unfortunately, like attacking the nitrogen, here you're putting negative charge. But again, you're going to the nitro. You guys have seen nitros time and time again. So to attack here, to put the charge on that and deprotonated, either one is fine. It's whatever you guys want to do. I'll accept either answer. But I like just going from this species, even if it's not exactly what's happening, because from my standpoint, this is a cationic species. It's much more active, and it gets you directly there. Okay, so this is sort of, again, often called HONO generation. It's a nitration process between aryl groups and nitric acid and sulfuric acid. Okay, so the point that I want to make is again, nitric acid isn't going to itself react, but you generate this more active species. Okay. All right, the one other one that we'll discuss is very, very, very similar. We'll through a few of these reactions, and then we'll discuss regioselectivity. All right, so this is going to be the synthesis of sulfonic acid. Okay, so this is a benzyl sulfonic acid. Again, we've seen the importance of these, for example, as acids in themselves, but they can be turned into other things, and so it's important sometimes. Again, the source of where this sulfur is coming from here is ultimately going to be SO3. And so again, it should be fairly obvious here what's happening. Is that the sulfuric acid is now going to activate this system through standard acid-base type chemistry. Okay. It's going to be something like this. Again, the overall species is now, that's the trend that we're seeing. It's cationic in nature. Sulfur is now positively charged, right? And what this, in essence, allows now is and again, when it reacts, right, what's going to happen is you're going to make a bond between one of the carbons within an alkene, leaving behind the carbocation. Again, this should be fairly redundant now. Right, and then we're going to sort of deprotonate it, redriving aromaticity. Generating the sulfonic acid. Okay? So again, this is analogous. They should all sort of, we've seen now what amounts to 4 different things that we can put at this position. It should be feeling repetitive. It should be feeling redundant. You should be getting bored. Right? I am. Because again, in each case, it should be the same thing, right? I am just repeating myself over and over and over again, and so they should all feel like the same reaction. And that's the point that I'm making. I'm not really getting bored, but maybe a little bit. But again, the point is that we can add a bromine or a chlorine. In both cases, we're activating that species. If you want to think of them as the cationic in nature, they will be. We can add nitrogen at that position through nitration. Again, same thing that's going to happen. You're going to activate that, generating a cationic-like species. Elimination to re-aromatize the system. Making the sulfonic acid, again, you're going to activate it, you're going to add to it, and then you're going to aromatize. So it's the same thing. It should be repetitive. So you're doing the same thing. You're taking the benzene, you're attacking something that's been activated, and then you're re-aromatizing the system. Okay? So we're almost done. But I think what I'm going to do here is I'm going to sort of ask you guys to sort of predict this next set of reactions. So we've discussed how we can add bromine, chlorine, sulfur, nitrogen. But perhaps the most important bond that we like to make, right, is which one? The carbon-carbon bond, right? Carbon-carbon bond is one of the most important things. So these are all heteroatom carbon bonds. But now what we're going to ask is we're going to show you a few examples of carbon-carbon bond forming reactions. So they're so important, so much more important than what we saw in the past, that actually people get names after themselves for these, and these are going to be called Friedel-Crafts alkylation and Friedel-Crafts acylation. Okay, and formally what both these reactions are reactions where we are effectively going to have an alkyl group as our cationic species. So again, we saw sort of cationic bromine, cationic chlorine in essence. We've seen cationic in nature sulfur, cationic nitrogen. In this case, what's going to happen is we're going to have cationic carbon. And again, it should feel like almost the exact same reaction, in part because it is. There's going to be no real fundamental difference between this reaction and, say, for example, bromination. In fact, it's oftentimes the exact same types of reagents. The only difference is that we're going to have a carbon bond. Okay? And so if I sort of told you that, if I just said that, let's just say a standard alkyl chloride, like let's say, for example, that we wanted to add a propyl group to this or something like that. Our standard R group there, we would know, right, that chloride isn't going to, alkyl chloride is not just going to react, right, with a double bond on this system, right? So we need something that's going to activate that alkyl group to sort of make it cationic in nature. And the nice thing here is that, unlike the sulfuric acid and the nitric acid, we had sort of lone pairs, right? Well, this is lone pairs as well, but what I mean is we have like oxygen bonds and we sort of propane them both with sulfuric acid. In this case, it's a halogen, so we can draw back to the sort of types of reagents that we were using for the bromination and chlorination. In a lot of ways, it's the same thing. The usual choice one here is usually aluminum trichloride. Which is, again, just a Lewis acid choice here. If you accidentally put iron trichloride, I honestly wouldn't care. It's the same concept here, and I think that's the most important thing, is that you take this molecule, it doesn't react by itself. You add in this Lewis acid, and suddenly it reacts. So if I were to ask you guys to propose a mechanism for this based upon what you learned from the bromination chemistry, hopefully you should be able to do that, right? So let's try to do it, and I want you guys being mentally proactive here as I do this. And so the first step in each of these was not necessarily have anything to do with the starting material at that point, right? Or the benzene, right? In both cases, what happened is the reagents reacted together, right? What type of molecule is aluminum trichloride? Lewis acid, right? Where are the lone pairs that this Lewis acid could bind to? On the chlorine, right? And so what's going to happen is the first step of this, right, is that our R chloride is going to react, right, and is going to coordinate, or we should say, to that aluminum trichloride, right? In this way, we sort of have a negative charge there and a positive charge on that chloride. And so we could either, again, as we did with the bromine, we could either react from this intermediate, or what I like to do is just actually draw the sort of extreme resonance form, if you will, where we in fact break this and imagine it as a full-blown carbocation. We get tetrachloro, aluminum, counterion. Right? We see this, we say, now it's really active. Now it can react with this system. Right? And again, this is where it can become a little bit tricky. We can try to react it again from that aluminum chlorine bond if you want, because you do need something that can take it off. I'll just keep it simple. I'll just stick to chloride. And the net result is going to be an alkyl group at that position. Okay. So this is yes.
Is it for these reactions?
So the question was asked: is this only with benzene? What do you think? No, it does it with any of them. So yes, this is all aromatic. We just are showing it on benzene and reactions of benzene. But certainly you can imagine a lot of these transformations can and do take place on other molecules.
For example, like fluorine or nitrogen. One of the nitro aromatic compound,
Sure.
Does it react at the nitrogen with one pair, or does it react with the double bond?
It's a good question, and there's not a direct answer. Depends upon the type of molecule and sort of what we have. In fact, nitrogen often serves as a Lewis base to actually promote some reactions of this sort. We can talk about that offline, but yeah, it's more. I can't give you a definitive answer. I would say both at this point, but again, it would depend. Okay, that's if the R group. So the important point here, and I may just move on because again we are getting repetitive here. But the only difference between a Friedel-Crafts alkylation and acylation is that the alkylation, right, is if, just like it sounds, it's an alkyl group. So what we're talking about here is, perhaps it's better to talk about the acyl group first. You guys know what acyl groups are? An acyl group would be something from like an acyl chloride. Okay, so if you have an alkyl chloride and you use this would be acylation. These you can imagine when you actually look at the cationic species, it's often good to draw it that way as the cation rather than somehow coordinate it, in large part because you have a really nice species that you can generate like that, where you have lone pairs that help further stabilize the system. But this would be an acylation. And again, if it's just sort of anything else, right, if you have a chloride, say for example, you know, and this is something, who knows, but some case where that's not a carbonyl or it's just an sp3 center adjacent to it, that's going to be alkylation. Okay. Again, those are just names. They shouldn't necessarily affect your ability to rationalize these both, which are formally both generating cationic in nature alkylating agents. There's one more that I do want to discuss in addition to these that you may be able to in fact predict right off the bat. Because what we've been doing here in the Friedel-Crafts cases is that we've been generating cationic carbon, right? We've been generating carbon-based cations, right? And you guys have seen carbon cations generated in the past in some of the chemistry that we've done. In fact, it's some of the earliest chemistry that you guys learned, right? And how did we initially learn to generate carbon cations? What was some of the starting materials that we used? Maybe this is a, what's that? Cation, right? If I wanted to just say, for example, generate a cation that looked something like that. Maybe they had water out there, for example. What might be my starting material that would lead to that cationic species? Pi bond, right? So this would in essence come from pi bond, or in other words, an alkene, right? So we basically learned in the past, right, that if you take an alkene and you treat it with an acid, and say, for example, right, this should be, everybody should remember this, right, but if you have, say, for example, an alkene, you treat it to sulfuric acid and water, right, what's going to happen is you're going to add the water across there, right, going through a cation. And so you may predict that in essence, if you were to use an acid and say, for example, you didn't have water around, but instead you had, say, for example, benzene as your solution, you might imagine these might have things would happen, right? So if I were to, instead of saying sulfuric acid and water, or some acid and water, if instead of saying acid and water, I said, say, acid and, say, for example, benzene, right? You might be able to predict what's going to happen here, right? We've effectively generated a cation, right? So what's going to happen here, right, is that will react. And once that reacts, we're going to alkylate it, and we are going to get to another aryl alkylation product. All right, so let's rehash a little bit here in terms of what we discussed today, and then we'll get into the next part, which is, I think, starts to get a little bit more interesting, and that's the aspect of regioselectivity. So in all these cases, all that we've discussed, right, is that we take benzene, and what we do is we treat it to a really, really, really strong electrophile. What happens in that chemistry, right, is that one of the pi bonds in benzene, again, you need a really good electrophile in these cases because, as we've stated, aromaticity is an energetically favorable process. So you need something that's going to make it a really strong electrophile. So again, in the case of bromine, right, we add iron tribromide, which soups it up and makes it, you can think about as Br+. Chlorine, you can think of FeCl3, soups it up, makes it Cl+. Nitric acid, right, you do it in the presence of sulfuric acid. That degrades it to this HONO, for example, or just the sort of the NO2 with a positive charge on it, if you want to think of it that way. But again, either way that you go through that, it's a much more active species than the nitric acid alone. Sulfur trioxide, right, in terms of that compound, you basically treat it with sulfuric acid. That's going to activate SO3. Then you add into it. Alkylation, same thing. Treat it with a Lewis acid. So you see the trend here, right? Treat it with a Lewis acid. You make carbocation extremely active compound, which is hot enough that it can now react with the benzene. And then in this last case, same thing, just a new way to generate a carbocation that can react ultimately with benzene. And so, for pretty much the last 40 minutes or so, 50 minutes, I hope that you guys can all convince yourself that I basically just went over the same reaction over and over and over again. Okay, so they should all feel like the same reaction. It shouldn't feel like too much. Get that list down of different electrophiles so you can treat with it, recognize what the products are that are on it, and you should be good with this material. That takes a little bit of, I guess, memorization, if you will, but you should, again, be able to lump those all together, so it should just feel like one big set. Where you want to move on and start using your brain a little bit more is going to be, and we'll start with it today, and we'll sort of finish it up with it on Wednesday. But it's this sort of idea of the effects of the substituents that we have on these groups, and ultimately what effect that will have on it. So benzene, that should be fairly easy, right? We put one group on there, we're done. But if we have a group on there, if I already have something that's on there, I'll just say, I don't know, just because I don't want to give it something that's going to confuse you guys, I'll just say there's a ball on there. There's a ball. Magical ball. Looks like a clock. Right? So I'll just, you know what I'll do? I'll make it a blank box. We don't know what it is right now. It's a box. Anything can be in that box. But the bottom line is that when we take this molecule and we treat it to our E+, right, there are, in relationship to that blank box, the electrophile could effectively end up at 3 positions in relationship to that. Right, we have the position right next to it. Okay, this is going to be a position that we call ortho, sometimes abbreviated as creatively as O. Sometimes it's this position here. It's going to be considered meta. And the last one, again, because it is symmetric, the last one that we have, we keep going around, we're going to be in different positions, but the last one's going to be para. It's going to be P. And so again, this is nomenclature. Sort of remember these terminologies in some way, however you can remember it. But these are really the only 3 positions. Again, if we keep going, right, then that's going to go back to meta. That's going to be ortho. So basically, it's the distance from that carbon that we're on. What's the sort of relative functionalization of this? Now, it turns out that electrophilic aromatic substitution is a fairly chemoselective reaction based upon what this group is. Okay? And this largely comes down to what we were kind of talking about earlier, but again, this is where you guys have to get good at drawing mechanisms and seeing these mechanisms. Right? But if this is, say, for example, let's say a methoxy, OMe. If we're going to think about the intermediates that each of these would lead to, okay? We're going to have intermediate resonance forms right? If that's our methoxy, if this is our E, right? If I react the E at this position, say for example across this alkene, where's my positive charge going to be? It's going to be there, right? I react my E at that position, where's my positive charge going to be? It's going to be here. And likewise, if I put that group at that position, it's going to be like that. Okay, so these are the intermediate carbocations that we can draw. And it turns out that by looking at these intermediate carbocation species prior to the elimination, you should be able to predict the products that form. Okay? So I'm going to leave you guys with that and not tell you which one they lead to, but what I want you guys to do for next class is we'll revisit these exact resonance structures, but I want you guys to sort of convince yourselves that some of these are more stable than others. Again, there's only 3, so I can't really give away, but sort of you should be able to predict which one of these, if not multiple ones of these, are the same